Thank you, and also thank you to Kevin for preparing the transition to my presentation. I should start by acknowledging the contributions of my co-authors. While all other presenters have done their work alone, I had significant help from my co-authors, which is particularly interesting since one of these projects is already terminated quite a while ago. Jerry Hämäläinen, he still has very fond memories of his project and was willing to support the proceedings and the presentation. So I would like to acknowledge that. I would like to start my presentation to put you all in the mood for reactor safety with a quotation from a safety manual published by the International Atomic Energy Agency in Vienna in the 90s. I think we all agree with the first part of the first sentence of the paragraph I'd like to quote. Effective maintenance is essential for safe operation of a nuclear power plant. That's obvious. And they then go on to describe the perimeter of safety relevant components. All plant structures, systems and components having a bearing on safety. Now, for most of us, what comes to mind when we read this certainly the pressure vessel, the primary loop, steam generator, maybe main coolant pumps. But you will see in the course of my presentation that the projects that are covered by this presentation go a bit beyond this intuitive definition of safety relevant components. And the paragraph closes like this. Safety relevant components, well, as they are when the plant goes into operation. In the trade we call this the pre-service inspection, but also after commencement of operation, and this is where a long-term operation gets into place. How to make sure that the safety relevant components keep their structural health throughout the entire life of the plant. So now you're in the mood. This is the outline of my presentation. I will start with a description of the safety systems covered, the scope of safety systems covered by the 4 projects in my project portfolio. Although this is meant to be cross-cutting, I would like to give a quick picture, a photo, a snapshot of each of the 4 projects covered. And we will then have a look at a comparative look at the scientific challenges these projects faced, their industrial impact, how they managed to get end users implied on board, and also the link to academia, which is quite important. And I would like to end with, well, lessons learned is maybe a bit soon because most of the projects are running for 18 months now. But a few observations and follow-up issues which can be derived from these preliminary observations. Okay, which safety systems are covered? Now, NOMAD and Advice cover the components that intuitively come to mind. NOMAD deals exclusively with the pressure vessel, while Advice also covers parts of the primary loop, all parts of the primary loop that involve, let's say, difficult materials. Now, TEAMCABLES goes one step further and deals with cables. Now, you might say that's surprising at a first look because the cable is a passive component. What can go wrong with the cable? We'll see about that. And Harmonics, the only project already terminated, takes this again one step further and deals not with a physical component, but with software dealing with safety-relevant functions in the plant. NOMAD, well, all these projects have more or less fancy acronyms. NOMAD stands for Non-Destructive Evaluation of Operation-Induced Material Degradation. I hope I got that right, almost right. And it starts with the observation that today we consider the pressure vessel to be the only component of a plant that cannot be replaced. 30 years ago, we considered steam generators to be not replaceable. We didn't design them to be replaceable. Well, we had to, due to long-term operation. Today we know how to do that. But for the plant is still considered the only part of the primary loop which we cannot replace And for this reason, it deserves special attention. And the failure mechanism, the aging mechanism that determines the useful life of a pressure vessel is irradiation-induced embrittlement. And, the problem is that, as you all know, in a pressure vessel, the base material is not directly accessible. We use a cladding for corrosion protection, and any assessment of the actual irradiation-induced embrittlement has to deal with the presence of this cladding. And this is exactly what NOMAD tries to achieve. It does this by carrying out a systematic study of the correlation of the microstructure, the mechanical properties, and this is done through destructive examination of test samples, the neutron irradiation conditions, controlled irradiation in experiments, in terms of accumulated dose over the lifetime, and the actual properties that can be assessed using non-destructive evaluation techniques, such as ultrasound, eddy current, and micromagnetic evaluation. Now, the project did not start from zero. We do have an existing database, but it's not complete. It's not complete, and but it is complete enough to know that the problem at hand is particularly difficult. We know this is a tough one. NOMAD aims to complete the existing database, since we want to use non-destructive evaluation techniques and the material is not homogeneous, somehow we have to deal with the heterogeneity of the material to make sure that the NDE techniques used are robust with respect to these heterogeneities, local heterogeneities. And after having said that, I think it's obvious for all of you that this is a massively experimental project. Advice, this is the project I am coordinating, so I'll try to be brief on that one. ADVICE stands for Advanced Inspection of Complex Structured Materials. Complex structured materials are very common in nuclear power plants. While we have learned to deal with the cladding in ultrasonic inspection, but welds, in particular transition welds between different base materials, can be tricky. Then we have repairs. In an aging plant, repairs do take place, and the transition between existing material and these ground out regions, which are then completed, filled during the repair, pose problems. And then there is the issue of cast austenitic stainless steel. I call this the holy grail of ultrasonic inspection. The microstructure of these corrosion-resistant alloys does limit the performance of what can be done with ultrasound. And in some cases, in particular for cast austenitic stainless steel, the structure of which is shown on the bottom, in some cases we have to resort to alternative techniques. I'm talking about radiography, which is other problems, which is highly disruptive and which also poses a health risk to the gamma radiation used. The project readily admits that there is no silver bullet to solve this problem. There is no single step change that will allow us to replace radiography by ultrasound. Instead, we take a more modest approach, and we believe that incremental improvements in a number of techniques, a number of steps, will allow us to increase the inspection depth for these components, and in some cases enable for the first time the ultrasonic inspection of these components. I will not detail all these, just the first bullet point maybe in situ characterization of materials. Today, when we develop an inspection procedure, we do this on representative materials that are supposed to be manufactured using the exact same procedure as has been applied in the actual plant. But if this representativity is not given, we make a mistake. And if we are able, by in situ measurements, to refine what we already know about the component under inspection, we're able to improve the inspection quality. Okay, TEAMCABLES. TEAMCABLES deals with the long-term operation of cables. In a typical 900 megawatt generation 2 plant, as we have plenty of them in operation in France currently, we have about 1,500 kilometers of electrical cables. That's a lot. Now, I said 5 minutes ago that the vessel is the only component that cannot be replaced. Technically, it would be possible to replace these 1,500 kilometers of cable, but this is not an economically viable proposition, so we can't really do that. I should probably start by saying it's not the actual copper in the cable that's aging, but it's the insulation and the jacket, the insulation that ages. And once this insulation is gone, the cable can no longer perform its intended function. And the aging of this insulation depends on the ingredients used in the polymer in the jacket. And yes, we need a means to predict the lifetime of this insulation, depending on the components used in this polymer. This is what is developed in this project. So polymer aging mechanisms need to be identified. Another important point is today the cable performs under nominal conditions, which are well known: constant temperature, pressure, etc. We have to be certain that the cable is also able to perform its function under accidental conditions, which are quite different: higher irradiation, higher temperature, there may be vapor, etc. Yes, the project aims to develop aging models, which are multi-scale models, which deal at the same time with the mechanical properties, the physical and the electrical properties. The project also aims to contribute to standardization of aging mechanism evaluation and of the NDT techniques used to assess the actual state of a cable. To obtain a lifetime prediction, a remaining lifetime prediction. The fourth project in my portfolio is harmonics. The other three projects were Horizon 2020 projects, which started in 2017. This is a Framework 7 project, which is already terminated, as I said in the introduction. And it starts from the observation that it is impossible, it's a fact of life, we have to live with, it's impossible to prove, to demonstrate that software is completely safety-free. I think this pragmatism is a key theme in this project. It focuses on instrumentation and control systems that perform safety-relevant functions. And the project aimed to develop realistic, practical, pragmatic approaches to assess the reliability of software used in these safety systems. Software verification and validations. You all know the difference between verification and validation when it gets to software. Software safety justification, and it means to quantify the actual reliability of software. You have to be able to put a number next to the reliability of the software. It's not sufficient to have just a qualitative evaluation of the reliability. Okay, then there is, we have to take the software lifecycle into account. Now, the word processor you use in your computers has a software lifecycle of a few years, 3 to 5 maybe. For scientific software, I'm thinking finite elements here, we have software lifecycles of 20 years, which is quite a lot, but with a nuclear power plant, we're talking about 40, maybe 60 years. So this goes beyond what we encounter in simpler systems. The project also aimed to demonstrate the feasibility of the proposed approaches in the field. It's one thing to develop a procedure, it's another thing to demonstrate that it can actually be applied in the field. And they got the regulators involved from the beginning. That's an important point. Okay, now I would like to compare these 4 projects under different aspects. This first slide covers the scientific challenges. I will not read all this to you. What we can say is that the 3 projects dealing with actual physical material, physical matter, they all had to have to deal with the understanding of aging mechanism, or the problem at hand is quite different for harmonics. which deals with the problem of how to formally justify extremely high reliability figures, considering that today we have no universally accepted approach to quantify the reliability of software. TEAMCABLES and NOMAD, they face the challenge of accelerated aging. Kevin mentioned this on one slide as well. That's an issue. In these projects, we have to accelerate the aging cycle and simulate aging of 20, 30, 40 years within a few months, which is a problem. NOMAD and Advise, well, they have to identify highly sensitive and robust ultrasound NDE, which is little affected by the microstructure. And I think the last line is a mistake. What I should have done is extend this through all the 4 projects, because ultimately all of these projects have to gain acceptance, have to convince the regulators that the solutions they propose are viable. It's not only true for Harmonics and Advise. NOMAD and TEAMCABLES will also have to deal with this at some point in time. Industrial impact and end-user implication. Well, most projects organize seminars or a symposium, something like that. TEAMCABLES is the one project that stands out since it goes all the way. In fact, they identified that they have to address different publics. They have to address researchers. They also have to address operators, and these different publics have to address differently. It's important. Another common theme for Advise, NOMAD, and TEAMCABLES is that they have the ambition to include not only Western-style technology, but also Russian VVER type reactors. They use different materials. Their steam generators are different. They don't have cast elbow pipes. There are many minor differences, and in order to get access to material samples, they have Eastern European partners operating VVER plants in the consortium. That's important. Harmonics had a link with the Chinese project, which started in a quite promising way, but eventually did not yield that much. So I will not go into detail. What else can I say? Yeah, all of Advise, NOMAD, and TEAMCABLES, they have a collaboration with EPRI. EPRI is in some form or another involved, maybe like in the advisory board. And all of these projects also benefited from the support of Nugenia. Nugenia was involved, was helpful, and in finding the right consortium, streamlining the proposal, eliminating parts of the proposal which went beyond the scope. And these projects are still followed by Nugenia as well. Okay. Academic involvement. I struggled a bit with this. In the preceding paper, you find a paper of the number of PhD students, the number of postdocs, etc. These numbers are changing. Last week, another PhD joined Advise. All of these also have 1 or 2 universities on board. NOMAD and Advise strongly collaborate with UK universities, and we will regret them after Brexit. But I don't think this table really covers the essence of what I want to say. This is a picture taken in April during the visit of the young man in the middle. He's from the University of Bristol. He came to our laboratory for a week to carry out measurements on industrial sample. He worked with our technicians. I'm not in the photo. I'm not even the guy who took the photo, because my added value would be non-relevant. What I want to say is that this kind of collaboration is an opportunity for these people who are the next generation to constitute their own network. I got mine. They have to construct theirs. And the young lady you see on the right, she will join Bristol for this summer. She will go there by the end of the month and apply the technology developed at Bristol University on EDF samples. Okay, I would like to conclude with a few observations. Well, it has been said a number of times, the lifetime extension of current generation 2 plants, currently in operation, has become economically viable for a number of reasons, with capital cost, etc. You know this. Now, at the same time, the long-term operation of the lifetime extension of these plants does raise issues, and some of these issues have motivated the emergence of the projects I just covered. One important observation for me, this is a personal thought, is that for these generation 2 plants, the assessment of their health has often been designed as an afterthought. The primary design directive was for the component to carry out its function, to perform, but the NDE part, the assessment, has been designed later, yes, as an afterthought, instead of being an integral part of the design, which is different in other disciplines. And well, once I have said that, once I've said all that, I think I can derive 3 conclusions. The first, today most of the assessment of the structural health is done using NDE at scheduled intervals, which are fixed, and we fix this inspection frequency from what we know or think we know about the aging. Continuous monitoring of the structural health has demonstrated added value in other industries, I think in particular of aviation and petrol as well, as a complement to these in-service inspections at fixed programmed intervals. And I think this is something that will have an impact on the nuclear industry at some point in time. Then there are aging models. We have learned a lot about aging models. We refine them, and if we get better, they will at some stage allow for predictive maintenance as opposed to scheduled maintenance as it is now. Now this poses a different problem. If we have data coming from NDE, scheduled maintenance, data coming from online monitoring, somehow this has to be aggregated in order to deduce useful conclusions. We'll see about that. And the third point I'd like to state is that, yes, inspection-oriented design has to be considered at manufacturing and for replacement components. For the new build, we do this, we've begun to do this, but for replacement components of older plant, this is something that is only just emerging. For instance, if an elbow pipe was to be replaced, would it be replaced by a cast component, or would it rather be replaced by a forged component? These are thoughts that are important. And that's almost my last slide. I would like to conclude with this picture taken at the second annual meeting of my project. Now, I took a similar picture at the kickoff meeting, and where you see everybody just aligned, 2 rows, very proper, somewhat military, if you wish. What you see here is, if you look closely, people have started to interact. These 2 guys to the left are from the University of Bristol and the Kaunas Ultrasound Institute, and they were just talking about a collaboration. In the middle, you see my colleague who discovered the experimental means of a facility in Germany, in Germany. And what looks as I was flirting with this girl next to my side is in fact a discussion about how the guided wave technology that is developed at this institute might be beneficial to EDF. And yes, I would like to conclude with this picture. Thank you.
Thank you very much, Andreas. Questions, please? There.
Thank you. As a co-reviewer of your paper, I have to say that I really appreciated the paper, so congratulations. I have just a question pending concerning the harmonics project. You say, and I perfectly agree with you, that software cannot in general be proven to be completely defect-free, and the validation process itself can also sometimes increase the risk of defects themselves. So, but you say that you have done improvement, you have done something, and you say that you trust in a progress. This is what I understand from what you have written. But anyway, this zero defect objective is not be achievable. So now we have, with the modern design of reactors, we rely more and more on INC, sometimes for safety too. You say that safety authority were part of the project. Which is their position on that topic? I think it's extremely important because the problem cannot be addressed by probability only. You have to address the residual risk. Residual risk is a problem which is connected to the acceptability of public. It is a societal problem. Thank you.
Yes, residual risk is a very abstract measure. We're dealing with extremely low probabilities, which are difficult to grasp. It's difficult to, if I indicate a failure frequency of 10 minus 8, what does this mean? It's a very abstract figure. I think what's most important here, and with harmonics, and what was recognized by the safety authorities, is the fact that they introduced means to quantify reliability. At the time the project was carried out, reliability of software was addressed in a qualitative way. Good, bad, satisfactory. The important thing is to be able to put a number, even if it's abstract and not easily to grasp for the public. The important thing is to be able to put a number next to the reliability, and to have an absolute measure which allows you to monitor an improvement in safety. To be able to say, yes, this is better than what I have done before, and it is better to that extent. So I should have put quantitative in both letters, I think.
Thank you. Another question, please? So, okay, thank you very much.
Thank you.
Yes. Now